Okay, so here we are in semester 1 of 2016. I'm talking about elementary matrices. As a pure mathematician, I think elementary matrices are really cool. They allow us to turn something that's a bit weird, like row operations, into matrix multiplication. So, there you go. Matrices are objects in their own right, algebraically. You can add them, you can subtract them, you can multiply them. Sometimes you can multiply them. Sometimes you can do inverses. You can do all the things, many of the things that you like to do with numbers, with matrices. And then there's these other weird things that you do with matrices, like determinants, that's a weird, traces, it's a bit odd, and row operations. Now, row operations are a layover from matrices being used to represent linear equations. But it turns out that the fact that your matrix represents a set of linear equations, regardless of whether you want it to represent a set of linear equations or not, it does. The fact that it does represent a set of linear equations is really helpful and gives you all sorts of useful information. And so what we'd really like to do is connect the row operations with the other stuff, algebra stuff about matrices. And so the elementary matrices are our way of doing that. They turn row operations into matrix multiplication. That's what they're for. Okay. And every row operation you do is the same. The effect of doing that row operation is the same as the effect of multiplying on the left-hand side of your matrix an elementary matrix. So, do a row op is the same thing as multiply on left by an elementary matrix. That's basically the big idea. So every elementary row operation has a matrix that instead of doing the row operation, I could multiply by that matrix to achieve the same effect. Now, why would you do that? Well, firstly, it's probably easier to teach a computer to do the matrix multiplication than the row operation. And secondly, it has some nice theoretical properties because it allows us to prove that our process for finding the inverse of a matrix actually works. Elementary matrices is the reason why that row operation thing for finding inverses works. So, how to make an elementary matrix. The definition in your notes says that an elementary matrix is what you get when you do a row operation on the identity, which is true, but I don't like it because you don't need to go through all that effort to find an elementary matrix. You just need to know what your row operation does. And first, I'm just going to show you something. Here is a matrix. Man, let me just make it a bit longer. Here is a matrix. I could do a row operation. Well, I'm not going to do that yet. I'm going to do this. So multiply it by 0, 3, 1. Actually 5, because I haven't used the number 5 yet. Okay. What will happen when I do this? That's my big question. I'm going to get 0 of that, and 5 of that, and 1 of that. Okay? And I'm going to get 0 of that, and 5 of that, and 1 of that. And 0 of that, and 5 of that, and 1 of that. And 0 of that, and 5 of that, and 1 of that. So what's going to happen is I'm going to get 0 of this whole first row and 5 of this whole second row and 1 of this whole third row. That's what multiplying a matrix by a row does. It does a linear combination of the rows of the matrix. And which entry here tells you which row is being multiplied by which number. So this is basically row 3 and 5 of row 2. That's what this row that I've just calculated is. So, all I need to do a row operation is to make a matrix that tells the universe and the person reading it how to construct the rows of the new matrix. So let me show you. If I wanted to do, you know, row 2 becomes row 2 plus 3 of row 3 on a 3 by whatever matrix. It doesn't matter how long the matrix is, it only matters how many rows it has. Okay, let's look. The first row of the elementary matrix will tell me what the first row of the new matrix is. So, the first row of the new matrix hasn't been changed. So, to make the first row of the new matrix, I'll have 1 of the old first row, and none of the old second row, and none of the old third row. And I haven't changed row 3 either. None of the old first row, none of the old second row, and 1 of the old third row will make my new third row. And my new row 2 will be none of the old row 1, and 1 of the old row 2, and 3 of the old row 3. That's the elementary matrix that does that row operation. Just telling the maths how to make the rows of your new matrix out of the rows of the current matrix. Now, it is actually true that if I did that row operation on the identity, I would get this answer. So if that makes you feel more comfortable, go for it, because I did that myself for years, and then I had this epiphany, and now I do this. However, this is not better than the other, it's just better for me. So if the other version's better for you, do that, because, you know, the worst thing you can do in an exam is use someone else's method that you're not comfortable with, because you'll just get it wrong. So, unless that's the only method there is, then just use it. Yeah, then you're screwed. That's how I would do it. So if I wanted to do, you know, row 2 and row 3 get swapped on a 4 by 6 matrix, then since it's on a 4 by 6 matrix, I'm going to need a 4 by 4 matrix. I haven't changed row 1, and I haven't changed row 4. And my new row 3 is my old row 2, so my new row 3 is none of row 1 and 1 of row 2, and none of row 3 and none of row 4. And my new row 2 is my old row 3, none of row 1 and none of row 2. Okay, which is the same as switching those two rows of the identity. Whatever works for you. Actually, in practice, I just write my matrix and copy the identity, but leave the 2 rows that I've 1 or 2 rows I've changed, and then just change them. And just for completeness' sake, to do row 1 is 3 of row 1 on a 2 by 5 matrix. Well, I didn't change row 2, and my new row 3 is 3 of row 1 and none of row 2. Right, that's making elementary matrices. Right, what are elementary matrices for? Well, they're really for, you know, theoretical interest. You know, I could create a matrix that does the row operation, and that practical interest if I'm a computer scientist. But for theoretical interest, they tell you that the process of finding inverses actually works. Because you can do the inverse of an elementary matrix really quickly. The inverse of that goes with the opposite row operation. So this one went with row 2 is row 2 plus 3 of row 3. Well, if I did that row operation and then I wanted to straight away immediately do another row operation to undo it, well, I just added row 3, I should take row 3 off. Like that. Easy to invert an elementary matrix. And this matrix, the row operation I did to do that was row 1 is 3, row 1. Well, if I did 3 times row 1 and I immediately wanted to do something to undo that, I would do a third of row 1, and that would get rid of the 3 that I put in there. And so I would just make the elementary matrix that goes with the opposite row operation, and that's the inverse. And the inverse of a row switching elementary matrix is the same matrix again, because you just switch them back again. So this was row 1 switches, row 2 switches with row 3. Well, the inverse will be, row 3 switches with row 2, which is the same thing. So you can always invert an elementary matrix by finding the inverse row operation. All right. Do I have enough paper to actually finish an example? So here's the thing. If I did any row operations at all, then there should be a single matrix that does all of those row operations at once, which is created by combining together all of my elementary matrices. What one matrix does, all 3 of row 1 equals row 1 minus 3 row 2. Row 2 equals a quarter of row 2. And row 3 equals row 3 plus row 1. No, maybe plus, something like that. On a 3 by 3 matrix. So I could create one matrix, it won't be an elementary matrix anymore, but I could make one matrix that produces all of those results. So I know that the result, if A is the original, the result will be A times an elementary matrix for the first row operation times another elementary matrix for the second row operation, but I'm working towards the left because they have to go on the left to make a difference to the rows. If I put them on the right, they'll make differences to the columns instead. And another elementary matrix there. And so the one matrix that does all 3 of them at once is this matrix. So E1 will be row 1 minus 3 of row 2. And E2 will be a quarter of row 2. And E3 will be row 3 plus row 2. Yep, one of row 2 and one of row 3. Okay, and so the one matrix to do all three is E1, E2, 3, E2, E1, because it's that number there, that one just there. Ooh, that's E1. And it is less difficult to multiply elementary matrices than it is to multiply other matrices, because multiplying on the left by an elementary matrix does a row operation. This one, that one, does multiply row 2 by a quarter, so that's what I'll do. And that one does add row 2 and row 3, so that's what I'll do. So each matrix will do its row operation on the answer to its right. Ta-da! Alright. I've run out of paper. Can I have another piece of paper from someone? And the final thing you might want to do is find the inverse of a matrix. Well, write a matrix as a whole as a product of elementary matrices.
So, David,
yep.
If we've got 4 elementary matrices, would they expect us to times them all together to equal the inverse?
I don't know. They might actually say, for example, find a product of elementary matrices which produces these 3 row operations. In which case, you don't have to find out what the single matrix is because it's currently written as a product, so you could leave it as it is. So if they specifically say find a product of elementary matrices, you can just leave it as it is rather than actually finding it. But the key is that it doesn't take that long, and I didn't even need to do this middle step because I just needed to start with that one and do both of those row operations. So, yeah. And actually that's the key working factor of how the inverse process works. Write that as a product of elementary matrices. It's like classic. I don't know whether they'll give it to you in an exam. It takes a little while. I can imagine them doing half of it for you, telling you the row operations and then whatever. Okay. I don't actually need this bit. If I don't want. So I'm going to write this as a product of elementary matrices. Not its inverse, the actual matrix itself. I know that if I can multiply enough matrices together with A to get the identity, then I can at least find the inverse as a product of elementary matrices. So the imagining that I have is that I'll have the matrix A, let's call it A, and I put an E1 on the left and another E1 on the left of that, and it's E2 and another E3 on the left of that, and eventually I'll get to the identity. So I have e's times a equals the identity. So all of those e's together is the inverse of a. It must be. So what I'm going to do is I need to do that backwards. But first I need to get to the identity. And I'm going to have to write down my row operations. I don't have to do them in any particular order. I can do them in whatever order I think is best to produce the result I like. So for example, I could do row 1 is row 1 divided by 3 here if I wanted. I could also do row 1 minus 2 of row 2 to get a 0 in a convenient spot. I'll do the traditional version. Row 1 is a third of row 1. And then I'll do row 2 is row 2 minus 7 of row 1. One minus 7, lots of 2/3, 1 minus 14/3. 3/3 minus 14/3 would be minus 11/3. All right, doing well. Row 2 is minus 3/11 of row 2. And then row 1 is row 1 minus 2/3 of row 2. I've managed to get to the identity using these row operations. So let's just ponder this. A times an elementary matrix. I'm going to write this, but I'm probably going to rub it out. Or maybe not. That's got its own elementary matrix. That's got its own elementary matrix. That's got its own elementary matrix, and that's got its own elementary matrix. So A times E1 times E2 times E3 times E4. When I did all those row operations, what I ended up with was the identity. So already, not that they asked me, but I can tell that this must be the inverse of A. Because when I times it by A, I get the identity. And a really convenient thing about elementary matrices is that if I want to know what they all are multiplied together, I just have to do all those row operations. So I can start with the identity and do E1 and E2 and E3 and E4, and that will tell me what the inverse is, because that's how to multiply elementary matrices together. And if I had done those row operations on the identity, that's why this would have been the inverse there. It's frickin' awesome. However, that's not what I want. I want A as a product of elementary matrices. Well, I've got a good plan. What I really want is the elementary matrices that go this way. If I can start with I and do its own elementary matrices, I shall call them F1, F3 and F4, and go backwards, it will produce A, and then I won't need the I, and A will be a product of those elementary matrices. Really cool. I just need to do these row operations backwards. But that's okay, because I know how to do row operations backwards. So the inverse of this row operation is row 1 equals 3 row 1, which has its own elementary matrix. And the inverse of this row operation is row 2 plus 7 row 1, which has its own elementary matrix. And the inverse of this row operation would be row 2 equals minus 11/3 of row 2, which has its own elementary matrix. And the inverse of this row operation is row 1 equals row 1 plus 2/3 of row 2, which has its own elementary matrix. And so therefore I've got that A is F4, which goes with this one. So row 2 didn't change, and row 1 was row 1 plus 2/3 of row 2. And F3, which is this one. Oh crap. Oh damn. I've written them backwards because I did F to get from I to A. I did this one and then this one and then this one and then this one. So I have to put them in that order. Sorry about that. F1 is 3 of row 1. Whoa, not a 0. F2 is row 2 plus 7 of row 1. F3 is minus 11 on 3 of row 2. And F4 is row 1 plus 2/3 of row 2. So just to point out to myself, that's F1, that's F2, that's F3, and that's F4. And the reason they're in that order is to get from I to A, I do F4, and then F3, and then F2, and then F1. That is an example. Yep?
Shouldn't that 1 and 7 be switched? Because
Yes, they should, thank you. You can tell I've been teaching for 5 hours straight. A good moral for that tale is don't do 5 hours of study continuously before you go to your exam. Yes. Well, being a morning exam doesn't prevent some people from doing that sort of thing. Yes. There's a great episode of Round the Twist where they have a spaghetti pig out and it's a spaghetti eating competition and tapeworm Tanya bows out after however many plates and she says, I don't understand it, I ate 12 plates at practice this morning. Yeah, don't do that. There's only so much correct arithmetic you can do in a row. That's elementary matrices, and thank you very much.